A what?
A prism?
Yep.
Yes,
You know what they do?
yes.
Bend the light.
They bend the light.
Good, bad, you go to
What
prison.
else do they do?
Separate the frequencies.
Exactly. That's the essence of propagation. 100%. So what happens here? That one there. There it is, right there.
Okay.
Wow.
The sun clearly is coming in from over there. And you'll see that the blue on the right is a shorter wavelength. So it gets bent a little more than the red on the left, which is a longer wavelength. So when you think about ultraviolet is off to the right,
Yeah.
and we don't necessarily see that. Infrared would be off to the left. And all the heat coming from the sun is infrared. But we also get visible light. But what you really need to learn from this is that one, the light bends. Two, it bends differently depending on the frequency. So when it comes down to it, is that the ionosphere is a big prism to us. It's a big prism that works on radio waves instead of on light. But light and radio waves are all electromagnetic radiation. So they follow all the rules of physics and all the rules of light bending through a refractive medium. And what happens is the speed of light is different in different mediums. So it's different in air, and then when it gets into the ionosphere, it slows down a little bit. And so what happens is, at that point where it changes, the light bends. And our ionosphere is just right that in some place, it bends all the way around and bends it back to Earth. So you end up with a picture like this. Let's see if I can. I don't know if I can get rid of that or not. Where we have a station here, trying to talk to a station out here somewhere, and the radio waves go up through the different layers of the ionosphere. Ultimately, they get up into the F layers. Along the way, they might get reflected back here by some of the lower layers. But for our purposes, all of the main radio propagation is done through the, or bending is through the F layers. And so you see it starts to bend a little bit right here, and then in the F2 layer, it kind of bends here. It's not just a straight reflection, because the density of these layers is different, so it just kind of keeps curving, curving, curving until suddenly it comes back to Earth. Got it? Okay, and so that's a lot of reasons why when you're talking to somebody on 20 meters, you can't talk to somebody in Iowa, but you can talk to somebody in Texas.
Yeah.
Because the distance in between is just right. So that's what SKIP is all about. We've heard about SKIP as long as we've been involved with radio. And I've been thinking about SKIP for over 60, 50 years now. And there's very little I understand about it, except sometimes I can talk to people in California just as easily as I can talk to people in North Minneapolis. What was I going to say here? Oh, these are just some resources. We'll come back to these in a little bit. I had this slide at the end. But if we wanted to, we could talk all day or probably all week about the ins and outs of different parts of propagation. Let's start at the top and see what we're talking about. We are talking about, we just showed you where light is. It's somewhere in here, and they talk about it as wavelength. We're accustomed to talking to frequency, but there's an inverse relationship between frequency and wavelength. So we're talking about, we're used to talking about 80-meter wavelength, or 20, 30, 10 meter. So they're all down in here, and there's 1 meter, but longer than that, down to 80 meters. Broadcast band down, whatever that is, 200 meters maybe?
300?
200, 300 somewhere, yeah.
200, yeah.
I guess it would be 300 at 10, or at 1
1,000, yes.
megahertz. But there's also a lot of other radiation that we don't even hardly aware of. The ultraviolet, we've heard of, and sometimes we get sunburned by it. Also coming from the sun are a lot of X-rays, higher, shorter wavelength, then you get into the gamma rays and cosmic rays. I'm sorry I couldn't get that. Well, I could. I guess I could get it. So it all fits on here. Come on. Maybe not. I'm not worried about that. Let's go down and look at. I was kind of fascinated by this picture, which shows that spectrum again from outer space. In other words, what's coming from the sun and other radiation sources. We see that there's an opportunity for radio waves to travel entirely through the ionosphere, through these layers of the atmosphere, and reach the Earth. So we can go both ways there. There's another window over here where light from ultraviolet to infrared travels all the way through the layers of the atmosphere and gets to Earth. But then you see a lot of gaps here where some of the infrared to microwave doesn't make it through the top layers of the atmosphere. And you also see gaps in here where some of the longer wavelength X-rays only make it through certain layers of the atmosphere, whereas the shorter wavelengths come a little deeper. And we'll get into the effect of that has on the ionosphere a little bit later. Refraction. We just talked about what happens with a prism. And in refraction, you have a source of light at the bottom, and when it goes through a place where it refracts, which is a change from the medium that it's going through to another medium, and that's exactly what happens in a prism. The light goes through here. It has to slow down as it's going through there because this doesn't conduct light as fast as the air does. So as it slows down, it starts to bend. And it bends based on what's called the refractive index of this medium and the other medium you're in. The ionosphere is just the same. It's a different medium, and as you go into it, any wave is going to refract depending on the frequency or the wavelength and the density of these mediums. But some waves, if they go through there, they're going to go through, and as they go through, they're going to be refracted a little bit. But as that angle increases, over to this example, all of a sudden, you get something called the critical angle, where that radiation no longer continues forward. It just gets on the top and it scoots right along. Or, as this angle increases further and further, you start to get reflection back to here. Now they call it reflection, but in our case, dealing with the ionosphere, it's really refraction. But the same rules apply. Got it? So you hear names, you'll hear later on something called the critical frequency, and you'll hear me talk later about something called the maximum usable frequency. And keep these three principles in mind as we get down there. You might remember having looked into an aquarium from the side, and if you look kind of straight above, you still see light over the top of it. All of a sudden you see nothing, you look a little further and all you see is like silver. That's where you hit that critical angle, and you can't break through that surface anymore. And then the first thing we have to come to understand is that there are several different layers of the ionosphere, and they all have different effects on radio waves. And I know this one's a little complex to understand. There's a lot of information on this slide. Let's see if I can make this any bigger. I don't think so. But if we start down, this is altitude above the earth in kilometers. So the first region we get into is the D region. That's the one closest to the earth. It's just a little less than 100 kilometers up, which is about 60 miles. And no matter what we're doing, all of our radio waves have to travel through the D layer in order to get up to the F layer. Got it? Because we can't get there without going through the D layer. So keep that in mind as we go forward. This is the relative electron density in there. These show the types of ions that are up there. They're a nitrogen and oxygen ion there. As you get up in here, there's some nitrogen ions, there's some oxygen ions, and it gets some nitric oxide ions. A lot of this up in the F layers are made by oxygen ions or nitrogen ions. We also get up into the point where we have helium and hydrogen ions up in the upper reaches of the F layer. And that's going to be important when we start to look at the effect that the sun has on the ionization in the atmosphere. And that's why things get better at night in some cases, and in some bands they get better during the day. Okay, there's a similar chart. Got it memorized?
Yeah.
Okay, good. Go on to the next one.
Is this
And
gonna
here
be
we'll
on the
just talk-
test?
What?
Is this gonna be on the test?
No.
No.
I'll give you all a pass.
Then I don't have it memorized.
Can you read that, or you want me to enlarge it a little bit? I can do that.
Solar radiation.
No, I guess I can't. Different wavelengths of radiation coming from the sun. Remember, we had X-rays that are shorter wavelength, we have infrared that's a longer wavelength. They have different effects on different layers of the ionosphere. Okay, so the very short ones, 1/10 of a nanometer to 1 nanometer, which are very, very strong X-rays. And remember from the first slide, they're the ones that make it lowest through the atmosphere. And they're the ones that get to the D region. Okay, and even these longer ones too, they ionize the D region. Okay, and those are the strongest coming from the sun when the sun is straight overhead. Because when it goes behind, we no longer have those strong short wavelength X-rays coming through the ionosphere. They get all the way down to the D layer, and they energize the D layer, and that affects propagation during the day. At night, the D layer goes away because the sun set and is no longer there, and they're heavy ions, and they like to recombine as soon as they can. As soon as they lose that energy that makes them ionize, that comes from the sun, as soon as the sun goes away, they like to recombine right away. So then you lose that D region almost immediately after the sun goes down. So we've all heard that happen on 80 meters and 40 meters. Sun goes down, all of a sudden you start working California, right? Doesn't matter whether it's 80 meters or 40 meters, you start getting through. High noon, you come here and you can hardly talk to Iowa on 80 meters. Okay, it's all because the D layer absorbs the energy, and keep in mind that the D layer is energized directly from the X-rays from the sun. So that's why it goes away at night. the solar flux. Should be able to get that so it shows the whole way. This is there. All right, well. When you go out to this site, no,
Go back and take the link again.
yeah, I'm not sure I will.
It'll work now.
No, I'll try it. When you go to this site, you get the daily solar site for the 7th of December. This is daily data. And you can see that the, what they call a 10.7 centimeter flux, which is, well, I'll get back to how that's measured. Right now, at this point in time, I guess it doesn't show the time, does it? Oh, no, this shows the day, that's all, it's 30 days. It varies from day to day. So today, it's 148. Back during the sweepstakes weekend, it was 176. We saw it at 282 back on the 17th. Before that, you had some really pretty big lows, okay? So the 10.7 meter flux, which is representative of all this radiation coming from the sun, it varies from day to day to day depending on what's going on in the sun, in the sunspots, and where we are in the solar cycle. Okay, this is about as high as we've seen it this year. Back in October, towards the end of October, there was a big contest, and when we were out at AIH, he said they made like 2,000 contacts on 10 meters. And 10 meters hasn't really been open much. So you can get this data. I want you to remember that it varies from day to day to day. And there's a lot of ways you can go out and get reports of what it is. And this is just another snapshot of what it looked like. I guess I took it last month. And the solar flux there was 161. Pretty good during that month.
The higher the number, the better then for?
The higher the number, yes, the higher the number, the better.
Both numbers?
The only one we're interested in at this point is the solar flux. This other one is the sunspot. It's a count of the sunspots. Okay, and what happens if you look at the sun, you see a little black spot, and sometimes that's multiple sunspots. That's why you end up with high numbers. But for propagation purposes, if you want to predict what it's going to be, you can go into a program and you can say, oh, here's the number of sunspots, and it'll go with that. Or you can say, here's the solar flux, and it'll go with that. And compute what you can expect as far as propagation. So now, I don't know why everything came out so big today. Yeah, I think I'm on a different. All right, okay, let's do this. Hang on, I'll just. Well, I'm not accomplishing what I want to do. I'm sorry about this, that I'm not showing you the whole thing. But here, this is called the critical frequency. And that's the limiting frequency at or below which a wave component is reflected by and above which it penetrates through the ionosphere or through an ionospheric layer. Remember the back old picture before was at a certain frequency, that wave is going to go straight up and it's going to hit the ionosphere and it's going to come right straight back down at us. Or the frequency will be too high and the wave will go right on through the ionosphere and won't come back. Or it will be lower, and in any case where it's lower, it'll come back. So sometimes you're on 80 meters the ionosphere is so thick and the critical frequency is above 4 megahertz, you'll have that reflection come right back to you. And that's where you can work all the locals around here on 40, 80 meters. And you can work a lot closer in stations because you're working close or under the critical frequency. Okay? So critical frequency is something that's reported regularly and you can pay attention to it. The higher it is, the more you're gonna be able to go up from 160 meters to maybe up to 40 meters and get some of that local stuff coming back. Now closely tied, or directly tied to that, is the maximum usable frequency. I know I can change this. I had it all sized for my computer, so I'm gonna do this. Let's see. There, now maybe we can read, no, we still can't get it all. Oh, yes, we can. I'll try that. Should be able to size this too, but I can't. Okay, the maximum usable frequency is the highest frequency that can be used between 2 points. Okay, a point here and a point in California. It's the highest frequency that I can use and still have propagation to California. Because if I go higher than that, the radio wave skips right on through the ionosphere. If I'm lower than that, I'll still get propagation to California. Okay, got it? That's why it's the maximum usable frequency between any 2 points, because if you're higher in frequency than that, the radio wave does not refract enough by the ionosphere to come back. Okay? Now, there's a catch to this, that I'm not showing this very well. I'm sorry about the
Can
size.
you change that 100% up in the core?
What?
Up in the toolbar towards the right, there's 100%.
I don't know if
Just
that'll
drag
help.
that down.
Ah, very good, thank you. It's the critical frequency. Remember we measured the critical frequency? What is that again?
Isn't that some of the maximum usable frequency where it reflects back?
The critical frequency is where it will go right straight up and come back.
Oh, okay,
It's the
sorry.
highest frequency that'll happen.
Okay.
So say that's 4 megahertz. The maximum usable frequency depends at the angle in which we're gonna come into the ionosphere. So if we go straight up, we may only get 4 megahertz coming back at us. If we're on 7 megahertz, it goes straight through the ionosphere because it's above the critical frequency. But now, if you take that same 7 megahertz signal and you start to go into it with a 45-degree angle, it's exactly, let's see if I got this up.
Square root of 1 half.
Okay. We take, yeah, it's that right there. So, this is what we're gonna divide the critical frequency by. I thought I had some examples here. Let's see here. Okay, I'm not sure I'm conveying this very well. If I go up on 4 megahertz straight up and back, then as that angle starts to increase, I start to look at the cosine of that angle, and it says that 7 megahertz going straight up is going to shoot through the ionosphere. If I go into it at a lower angle, based on this equation, 7 megahertz is going to, at some angle, start to bend back. Up here, it goes, shoots through, I start to tilt it down, and all of a sudden it's going to bend back. So the maximum usable frequency between 2 points is a function of what your angle's gonna be going into the ionosphere to give that bounce. And that's a function of how far apart these 2 points are. Okay?
So that worked out to about 6.5 in our hypothetical case?
No, what it says is that the lower angle you're gonna go into it, the higher the frequencies that will be bent back.
Yes. Which in our case would be 4 divided by the square root of 1/2, right?
Well,
Yeah,
it's,
it's 1.414 times
Mm,
4,
yeah.
so
Yeah.
yeah, so
Yeah.
well,
Yeah.
it's dependent on the angle.
Yeah,
So if we go in with a very low angle,
you got it.
okay, cosine of that angle, that's the angle coming down this way, is, approaches 0,
yes,
and we're using that to divide the critical frequency by. So let's say the cosine of that now is 0.1. We're gonna go at 10 times the critical frequency that we can make that.
yes, okay.
Maybe a way to look at it is when we transmit on VHF frequencies and we go straight line of sight,
Yep.
right? We're not really thinking about propagation or skip so much, but if we were to point the antennas up for satellite, it would go right through
It would go right through.
to the satellite.
Yep.
It'll go through anything at a 2-meter
Yep.
frequency, for example.
But what this explains is why we can work California on 15 and 20 and 10,
On a dipole, even though
When
the
the critical
radiation's
frequency
going off
is
at
4.
different angles, right?
okay?
Yeah.
Because the maximum usable frequency between here and California is a function of the angle that we go into the atmosphere to get back to California.
Which is a lot of different angles, but one of those angles will.
Yeah, but
will
only
hit.
one of those is gonna be exactly right on
Right.
California.
Right,
And now that depends on the height of the F layer.
right.
Because that may be 450 kilometers up there, or it may be 200 kilometers up there. If it's lower, we're gonna bounce back closer. If it's higher, the path is gonna be longer. Okay, and that's what's really goofy about these ionosphere, is that sometimes it's way up there, sometimes it's down low. It changes during the day, it changes as a function of the solar flux. So let's bring this back to something bigger here. I'm glad you noticed that. The K index, it has a measure of the magnetic activity and that comes as a result of particles coming off of the sun and passing through the Earth's magnetic field. And that has a disruptive effect on the ionosphere. So what it does is disrupt it. So what we really want to do is have very little magnetic activity coming through. And that's why we watch the K index on a daily basis. Because it's going to disrupt what would normally be good propagation from here to Australia. And it also makes it quieter. Okay, so I can't go into a deep explanation of how the K index works, except that we want to watch it. And the A index is a function of what the K index has been doing throughout the last day. Okay, and it kind of has a residual effect on propagation. And you can get forecasts from that. I'm going to take you to a couple other sites. But anyway, here's the definition of the A index relative to what the K index has been. If you have a K index of 5, you end up with an A index of 48. Okay, and typically, when we're looking at reports from WWV or something, we hear the A index and the K index. If you really want to dive dive deep into everything that's going on with the sun. Okay, and I hope I've established by now that the sun has a big effect on the ionosphere, and that's why we see so much difference from day to day, from season to season, from year to year on propagation that we use. Here's A indexes. Over the last 30 days. Here's pictures of the sun. Shows the sunspots. And you can see, in this case, a lot of these. Here's the solar flux index for today, 151. Let's see, they'll show the A index was 4 and the K is 1. This is a very good site if you really want to dive deep into every little bit of thing that might affect propagation. Now, what affects the F layer and what affects the D layer? Different lengths of X-rays. The very short X-rays, which are 1 to 8, and this is half to 4. These are shorter, the blue are shorter wavelength X-rays. So they penetrate deeper into the ionosphere and they affect the D layer. And so if you look at this throughout the day, you see that they grow during the day. Let's see, you have to know where this is relative. Oh, you can compute our time here and know. No. These are from satellites that are always seeing the sun. Okay? So you can see that the X-ray levels vary during the day. And you can see in this case, these are going to cause the D layer to increase as you get peaks on here. And what's that going to do? What happens with the D layer? It absorbs the lower frequencies. So all of a sudden, it may start absorbing 10 megahertz frequencies. Or if the D layer is not as thick, then 10 megahertz may go through it. You may have worldwide propagation on 10. It may go so high that it affects 14 megahertz, and you won't get propagation on 14. You got to go to 15, because the D layer during the day absorbs it. Let's see. You can get all kinds of data about solar flares. Let's see if I got anything else interesting to show you. But then the D layer is up there about 54 miles. Let's bring this back down maybe size there. D layer is low. It's ionized by strong ultraviolet and short X-rays. It absorbs medium frequency and high frequency signals. Disappears as the sun goes down. So propagation changes when the sun goes down. The E layer is further up in the atmosphere, somewhere between 50 to 100 miles. And the E layer has relatively little effect on our general propagation. We do get some scatter back from it, and sporadic E on various frequencies, but our main course of propagation is through the F layer. The F layer has 2 layers, and they, at nighttime, tend to come together. During the daytime, they separate into an F1 and F2. So sometimes you make it through the F1 layer, but generally you want to make it through F2 because it's higher. It's going to give you a much longer skip. The F2 layer can go way up high during the day and reach 360 miles, which, just to put it in perspective, this is where the International Space Station sits, somewhere in that elevation above Earth. So the F2 layer is really way out there. Now, I'm going picture to start with. Does it make a little more sense now? How these layers affect the propagation? This is really where we wanna get if we want long wave propagation. And there's also a specific distance here, a maximum distance based on the geometry of the earth. From here to here is a specific distance. This height can vary. Higher up it goes, the longer that skip distance is. The lower it is, you're skipping through this layer, you can't reach as far. Now, I wanted to put it all together in a PowerPoint, and then I went out on the internet and I just Googled presentations on high frequency propagation. And I found a whole bunch of really wonderful ones. And so mostly what I want to do is share with you that they're there, and they describe what I've been trying to tell you about today, is that it's affected by radiation from the sun, and there are three main layers. Here's another picture of it. I'm going to try to get this all together so that you can get these links. Because if you really want to dive into it, some of these are very, very good presentations. I just don't have time to go through every one of them in depth. But it kind of confirmed for me that I think I was on the right track in what I'm trying to present to you. There's the picture again. Virtual height, remember, is how high we think it is for geometry to calculate the distance between these 2 points. We talked about the critical angle again. It's okay, here's some that are above the critical angle, and look at this, they won't bounce back. But remember, as they start to go at a lower angle, they can get reflected back. And that's the effect of the maximum usable frequency between any 2 points. Let's see if there's anything else I wanted to show you on this. This shows what affects it, UV radiation. It's affected by the sunspot cycle, which hasn't been very good lately. I don't think there's anything else. Well, these are just good resources for you to look at. Here's another presentation. Does basically what I've been talking about here. Talks about the effect of the different layers. Now here's a fun picture. Let's see now, can I expand this size on this one? I don't know. Yeah, there we go. This is an ionogram. So they can measure what frequencies are going to go right straight through the ionosphere and determine what that frequency is going to be. So here we are, we're seeing this shows the critical frequency here. It's starting to get bent back. Over on this side is these are critical frequencies of different layers. Okay? So as we get out to the higher layers, which are the height of the ionosphere. So here we're getting up into the F layer. And so there's a notion that the critical frequency of the E and the F layers are much higher than the critical frequencies of the D layer, which is at a lower level. And what do we want to happen with the D layer?
Want to disappear.
We want it to disappear. So that we can use lower frequencies at night. Higher frequencies penetrate through it and don't get absorbed as much as the lower frequencies through the D layer. That's why we can use 20 meters and above during the day. And there's lots of, there's another calculation. It's a little bit different than what I showed you, but basically it has to do with the angle that we're going into the ionosphere that affects the maximum usable frequency. Let's bring this one up. Okay. Here, if the frequency is less than the maximum usable frequency, it reflects. If it's exactly equal to it, it comes right back down to the site. Okay, remember the maximum usable frequency is a measure of what's going to happen between two particular points. Here in California, rather than here in Colorado. Okay, because some days the propagation on a particular frequency is just fine between here and Colorado, and you never hear California. Has to do with the maximum frequency. So here, if the frequency is too low, we peter out. If it's exactly right, we make it to that station. If the frequency is greater than the muff, it does not get reflected back. It just disappears into space. So that's why we want to pay attention to the maximum usable frequency. And that varies during the day. It varies with the density of the F layer. It varies with a lot of different factors. Now, if you really want to get into in scientific terms, this is one from my university, Stanford Electrical. But the principles are all the same. It still talks about where the layers are. It talks about how they differ day and night, the D layer and the various F layers. This is the altitude. Remember, F layer is up there somewhere 400 kilometers. The D layer is down here. And again, this is similar to the picture I showed before. Daytime solar maximum. And this shows the altitude. And this shows a measure of the electron density based on the altitude. So these are there for references, and I'll try to get pointers in all of this so that you can come to the site and look at these. And here's another one. I think this one actually came from ARRL. There's the key layer. It can be mysterious. They're different during the day and the night. Why are they different during the day and night?
D-layer
D layer?
absorption.
Yeah. And the sun is gone, so we don't have radiation from the sun. And the sun that affects the D layer, when the sun disappears, the D layer recombines faster because it's different kind of molecules and they're much closer together. So it recombines. It's no longer an ion and an electron floating around there. Get up in the F layers and the sun does the same thing up there. It ionizes what's up there, the hydrogen and the nitrogen, the hydrogen and the oxygen and stuff, but it's much less dense, so the recombination of the ionosphere happens much slower, up and way up in the F layers. So that's why the F layer can linger overnight. And sometimes overnight on 20 meters, you have worldwide propagation. Because that F layer has remained intact. But the D layer is gone. Some bands are better for short distances. Why? Because critical frequency is, they're below the critical frequency. And so they'll bend back. Whereas if they were above the critical frequency, they would shoot right on through. And you can't bend back to Chicago location in that case. Here, even worse, they change tremendously from hour to hour and day to day. Now, how can you track these things? I've got a couple of let's see, I thought I had some good pointers. I already showed you solarham.net. It's got data from satellites that measure the radiation that's coming from the sun. And we know that the radiation from the sun is affecting the layers, and we know that the radiation from the sun changes from day to day, from year to year, and the stronger it is, the better propagation we're going to get, because we get a thicker ionosphere. As that radiation settles down at the bottom of the sunspot cycle, the ionosphere is not thick enough to support the bending of the waves. So we go for years where we can't use 10 meters because the ionosphere is not thick enough. And it's not thick enough because the sun isn't active enough. And you can go to these satellites on this solar ham site, which we went to before, and you can see there's a lot of sun activity, a lot of sunspots, the sunspot number there. So we expect heavier radiation, so we expect a heavier ionosphere, so we expect better radiation, we expect better propagation. We'll go back to one other. Okay. There's a very good, and I've used it for years, but I cannot find a good copy of it now to use. But if you can find it, it's W6EL propagation prediction. And with that, you can pick 2 points from here to Australia, and you can put in the solar flux index, or you can put in the sunspot count, and then you hit calculate, and up comes results throughout the day. You know, almost every half hour or so you get a row. So you look at points during the day, and then over on the right you start to see A or a B or a C. And if it's an A for 20 meters, it means you're going to have propagation there anywhere from 75 to 100% of the time, based on those solar conditions that you put in. So you put in solar flux and you put in the K index. And they'll come back and say, okay, 75% or better of the time, you're going to always have an open path to Australia at this frequency. Then as you go further over are the frequencies, and they start to go up. So you got one for 80 meters, you got one for 40, you got one for 20, and one for 15, and one for 10. And then you'll start to see that only during certain parts of the day, you might have an A on 20 meters. So that says almost any time on 20 meters, you're going to have propagation with those solar conditions. Okay? But you might have a C or a D or a B. You got a D and you're going to have less than 25% probability that you'll have that propagation. I wish I'd had this so I could show you, because it's one I use at home all the time.
Larry, have you looked at the Gaalaa cap prediction map?
I have somewhere along the line, I don't think I have a link to it here.
Okay.
But, yeah,
Right here.
5?
Yeah.
Okay, I got one more, and I showed this to you before, because if you really want to find out what propagation is like today, right now, there's this wonderful network of WSPR, can look on the map, and you can pick a band, 20 meters, and you can say, show me everything that's gone on in the last 10 minutes. So I'll update it with those parameters. In the last 10 minutes, stateside, we don't have any propagation to Europe. We've got a little bit to South America. So let's go down and say, okay, well, what's it look like in the last 6 hours? Take a look at that. Over the last 6 hours, we've had a lot of propagation to Europe.
But nothing right now.
What?
Nothing right now, it's kind of strange.
Well, that's what I thought too. All right,
Well, that was the last 10 minutes.
that was the last 10 minutes.
Yeah, it just depends on who's putting in reports.
It is.
Yeah.
And there may be,
Oh,
there
is
may
that
be,
when you don't have propagation, it's nobody reported, nobody
Yeah.
contacted.
There's no reported propagation.
Yeah, okay.
right now, there's no reporting.
Reported, that's the key word.
All right.
Yeah.
But we didn't have a tool like this 10 years ago. We just get on the air and we talk to our buddies, oh man, I went to Australia this morning at 10 o'clock. Now we can go on here and if you wanna set up your own station, do it, you know exactly what you're hearing. And I'm amazed that when I run 1/10 of a watt on Whisper, I'm heard all over the world. So I know I have propagation there. It may not be strong enough propagation to get there on CW or sideband, but at least there we know there's propagation. Any questions? Did I totally snow you? Did I put you to sleep? Did I help anybody? Yeah,
You know if clouds make any difference?
clouds?
Yeah, you say you have a heavy cloud cover. I talk in general about your,
I haven't heard any reports that affects HF at all. We know that,
It'll affect digital TV.
yeah, when you get up into the HF range or up into the microwave, I know there's some of the satellite feeds where people have trouble with rain.
yeah, like
You have a line of sight.
I'm only talking HF here,
yeah.
okay? VHF propagation is something entirely different and could be a study all to itself.
It's mostly line of sight anyway.
It's line of sight, but then there's all kinds of weird things
Right,
going
no,
on.
right,
So-
no. Fires,
So what I talked about today is just the normal run-of-the-mill HF propagation.
So what did you say the low, or the D layer, what was its altitude?
What it's what?
The altitude or elevation,
It's the
54
lowest one, so
kilometers.
it's basically under 100 miles.
100 miles?
Up.
Okay.
Between here and 100 miles,
Because there are some satellites that are on 29 megahertz.
yes.
And, you know, so I guess, you know, they're like 150, 200 miles up.
Yep.
And it must be right at that
Or-
frequency.
Let me back off to something on the D layer.
Yeah,
It doesn't, it affects the lower frequencies much more than the higher.
right.
So generally, it only affects up to about 10 megahertz. Okay, above 10 megahertz, we break right through it, because it is definitely a function of frequency. But on 4 megahertz, we know that it totally absorbs, you know, the paths between here and other parts of the country on 80 meters. So 29 megahertz, that shouldn't be affected by the D layer.
But then when the D layer goes away, then that whole 10-meter band goes away, because it just continues right on up.
The 10 meter is
At
not
night.
dependent on the D layer, it's dependent on the F layer. Okay, now what happens with that is that the F layer may get a little thinner at times, and at night it comes lower, and so that's all gonna affect the critical frequency and the maximum usable. Okay? Now, there's other catches that I didn't talk about. We talked about a single skip.
Mhm.
But what happens in real life is to get further than 2,100 miles, I don't know if that's the magic number or not, but to get further, you have to do a multiple skip. So you might come all the way back to the ground and skip, or you might, I didn't talk about this, but you might come back to the top of the F layer, or the E layer, and bounce off the E layer back into an F layer, and you may bounce several times that way. The W6EL has an option in it that will tell you how many skips you make and what layers you're likely to go through. Late in the evening, there actually is a path that, as the sun goes down, we start our first bounce is through the E layer, then it comes down, and then it bounces back up again into the F layer.
That's like the gray line.
We could talk, there's a whole nother aspect of this on the gray line. But that's part of it, is that, you know, the E layer starts to play a role in there. So if you can find that W6EL, or if I can find it, I'll let you know, but the last links I found to it are not working. And what I could find was, it boggled my mind, I thought it was time to take over my computer when I tried to install it. So I didn't trust it.
Okay, thanks, Larry.
Yeah.
Thank you.
We'll try to get this up online.